Hello, and welcome back to Physics 123, Quantum Mechanics 1. We are now on the last lesson for this chapter. So first, let's review some of the uh, concepts that we need for this last lesson. So we have derived the states of a particle trapped in an infinite square well potential, and we found out that the states are alternatively even and odd bound states. For the Dirac delta potential well, it has both bound and scattering states, and it only has actually one bound state, and its bound state is actually an even bound state. So we need these two concepts here, because for our last lesson, our potential energy well will have states that will approach an infinite square well and a Dirac delta potential well at some limits. So the last lesson will all be about the finite square well potential energy. So this is the finite square well potential energy. This is actually a more realistic version of the infinite square well potential energy. So the value of the potential is negative U naught, where U naught is a positive constant from negative A to A, and it's zero everywhere. So inside the well, the potential is negative U naught, where U naught is a positive quantity, and outside of the well, the value of the potential is zero. Now, unlike the infinite square well, which has an infinite depth, the finite square well has a finite depth. Its depth is just finite, it's measurable. Actually, its depth is U naught. The depth of this well is actually U naught. So the energy of our particle here, if we have a bound state, will be greater than negative U naught, of course. So negative U naught is the bottom, it's the floor of the ground floor or the bottom of your finite square well. And if the energy of your particle is positive, again, that corresponds to scattering states. But by the way, in this problem, in this lesson, we will no longer be considering the scattering states. Instead, we'll just be focusing on counting the number of bound states. So what are the general solutions now? So you will notice that there are three regions here. This region here, x is less than negative a, and this region here, from x is from negative a to a, and this region here, x is greater than a. So we represent the wave functions corresponding to those regions as psi1, psi2, and psi3. Don't worry, we'll actually not be solving the actual wave functions. We'll just count actually the bound states. So for x is less than a, the potential is 0, less than negative a. So we have this familiar simple harmonic motion equation. Again, since the energy is negative, then we let this whole term, including the negative sign, as our kappa squared. And the solution to that is, of course, hyperbolic functions, or e to the kappa x and e to the negative kappa x. For x is greater than negative a, similarly, 0 potential energy, and we will have the same solutions. So our linear combination coefficients are at f and g instead. Now, how about for inside the well? So for inside the well, the potential energy is now actually negative U naught. If you insert that in your time independent Schrodinger equation, you can reduce this to here. Again, U naught is just a positive constant. So since E here is negative and U naught is a positive constant, U naught is actually greater than E. Take note, negative U naught is less than E, but positive U naught is greater than the energy. So this whole term here actually is E plus unit is actually a positive quantity, and we let this quantity here excluding the we don't include the negative sign as our L squared, where our L is just the square root of 2m E plus unit over h bar. Take note, the kappas and the L's are all positive, are all real constants. So again, E plus unit is a positive quantity even though E is negative, since unit is greater than, unit is positive. Okay, so for side 2, the solution for this are, if you have negative sign here, the solution for that is sinusoidal. So in terms of, can use e to the ikx or ilx or e to the negative ilx, or you can also use sine lx or cosine lx. So here are now our boundary conditions. So it's generic boundary conditions. As x approaches negative infinity and as x approaches positive infinity, the wave functions must approach to 0. And specific boundary for this condition. So since again our potential energy function u is symmetric, if you will notice, it's symmetric with respect to this boundary here at x is equal to 0. Our potential energy function is symmetric. Then we can just use one side of our one boundary at x is equal to a boundary. So again, you can only do that if your potential energy function is symmetric. But if it's not symmetric, don't do that. Okay, so at x is equal to a, your wave function must be continuous. So meaning at x is equal to a, psi 3 and psi 2 must be the same. And at x is equal to a, the derivative of psi 3 minus the derivative of psi 2 is discontinuous. So they will have a difference. Okay, so using the first boundary conditions, we set a and g equal to 0, similar with what we did with the Dirac delta function. So be sure to watch that before watching this lesson. So again, in this lesson, we will only look for bound state. We will no longer bother looking for scattering states. So we'll only look for bound states, and we will not actually solve for the form of the bound states per se, but we will only count specifically the bound states. So we'll only count the bound states. So similar with what we did with the Dirac delta function potential, we first look for even functions, even bound states, and then in the second half, we'll look for odd bound states or odd bound wave functions. Okay, so this is an even bound state. So at psi 3, so psi 3 is just e to the negative kx, so exponential decay here. And then from negative a to a, inside the well, so inside the well, which of these two, this is the wave function inside the well. So which of these two is even and which of these two is odd? So of course, cosine is the even. So we use the cosine, we don't use the sine. We'll actually use this sign here later when we look for odd solutions. So we use the cosine from negative a to a. And then of course, since we have asymmetric potential energy function, we only use the one half of the well. So at x is less than 0, on the other side of the well, the wave function is psi of negative x. Okay, so we apply boundary condition 3. Psi must be continuous at the boundary. So at the boundary, so you have f e to the negative k a is equal to d cosine l a. Okay, we then apply boundary condition number 4. So oh, by the way, sorry. I may have misspoken earlier that the derivative is discontinuous. The derivative actually here is continuous because we no longer have an undefined potential here, unlike the Dirac delta function, which has an undefined value at one point. But this is just a finite squarable potential energy. It's defined at all points. There's no undefined values of u here. So the derivatives of both sides of the wave functions in both sides of the boundary must be the same. or is continuous. So the derivative of this evaluated at x is equal to a is equal to the derivative of this at x is equal to a. So you will get this one. Derivative of cosine is negative sine, so you have negative sine. Derivative of e to negative kx is negative k. So you have a negative k here. Okay, we will actually divide this equation here by that equation. Actually, that's very mathematically wrong. You divide actually this side of the equation here by f e to negative ka, and you do the same. But since f e to negative k is d cosine la, so you can actually so you divide this side here by f e to the negative k kappa a, and this side you also do the same. But since f e to the negative kappa a is also equal to d cosine la, so I can also do this d cosine la, right? Because f e to the negative kappa a is just equal to d cosine la. So doing that, this will give you negative kappa, and then sine la over cosine la is tangent. So you will have a tangent function here. Okay, so you have ka la tangent. So multiply both sides by a, you will have ka la tangent la. So if you will notice, k squared plus l squared, so square of this plus the square of this will actually just be equal to 2 mu naught h bar squared. Now, if you multiply a squared both sides of the equation, then you will have ka squared plus la squared is equal to this one. We can actually let z is equal to la and z naught as the square root of this function value here, so that this will become ka squared plus z squared is equal to z naught. This is just equal to z naught squared. So you can solve for ka here. You also have a value of ka here. You equate those two values, and you will get this transcendental equation. So again, this cannot be solved directly. This needs a numerical approach. But since we only need the number of states, which corresponds to the number of z's. So the number of z's, how many z's are solution to the equation, corresponds to our number of even bound states. Since yeah, the number of z's corresponds to our number of even bound states. So similar with what we did with the Dirac delta function potential energy, we plot the two functions. So this is tangent of z. Its value is actually undefined at pi over 2, 3 pi over 2 at integer multiples of pi over 2. And this is the function square root of z naught squared over z minus 1. So when at z is equal to 0, it's actually undefined. So this goes to infinity. It's asymptotic to the infinite up to infinity. It's asymptotic to this axis here. And then at z naught is equal to z, the value is, this is just 1 at z naught is equal to z. 1 minus 1 is 0. So the value at z is equal to z naught is 0. Okay. So there could be at least one intersection or at least one solution here, depending on the value of z naught. So if your z naught is greater than 2 pi, then you will have 3 solutions. So the solutions actually occur near z is approximately n pi over 2. So near pi over 2, near 3 pi over 2, near 5 pi over 2. It's approximately near, where n is 1, 3, and 5. So we will consider 2 limiting cases here. First, we have a wide, deep well. So if you have a wide, deep well, meaning A is the width of the well is very large. So A is very large. And if you have a deep well, meaning U naught, that's the deep depth of the well, is also very large. So that would make your Z naught very, very large, because A is very large and U naught the depth of the well and the width of the well A is very large. So if Z naught is very much greater than 1, then and your Z ends are approximately n pi over 2, then you can solve for the energy level, energy above the bottom of the well, En plus U naught, which is just approximately n squared pi squared h bar squared over 2m 2a squared. And you must have realized by now that this energy form or value is that of an infinite square well potential. So the finite square well will approach the infinite square well potential if you have a wide deep well. So if you have a wide and very deep well such that it now looks like an infinite square well, so its energy levels will approach that of the infinite square well. So actually in this case, in our case, the width of the well is 2a because it's from negative a to positive a. In the case of our discussion in the infinite square potential, it's just from 0 to a, but you can easily convert that to negative a to a, and we will get a result something like this. So this is the energy above the bottom of the well, because the bottom of the well has an energy of negative U naught. Okay. So second limiting case is we have a shallow, narrow well. So shallow meaning A is very small, the width of the well is very small, and it's a shallow. It's not that deep. So if you have a shallow well, so your A is very small and your U naught is very small, so Z naught is very much less than 1. So if Z naught is very much less than 1, so the value of Z is very much less than 1, so your function will look like something like this one. What happened? Something like that one. So there will still be one solution, and if in that case there's only one intersection or one bound state, so your Z naught actually here will be, say, less than pi over 2, and there will only be one bound state. So again, we are still on the even solution. So there's only one even bound state in that case. So in this case, the finite square well actually approaches the energies of the delta function well. Sorry, right? Because you have a shallow, narrow well. Your well is very narrow, such that it now looks like a delta function. So in the limiting case of a wide deep well, you approach an infinite square well. But if you, in the limiting case of a shallow narrow well, you approach the delta function well. Again, this is the property of the delta function. It has only one even bound state. You recall the previous lesson on the delta function here. Okay, let's now look for odd bound states or odd wave functions. So if this is your wave function here, so to construct an antisymmetric wave function, so at this point, so opposite, so like that. So we will now use the sign inside the well. The wave function inside the well is now sign because this is an odd function. So at x is greater than a, that is still e to the negative kx exponential decay, and on the other side of the well, at x is less than 0, it's a negative psi of negative x because it is an odd function. So doing the same thing that we did with the even bound state. So in the previous solution for bound states, we have tangent z equal to this function, but now we have negative cotangent z. That is our transcendental equation. So in problems like this, you only need to your solution will just be until the transcendental equation, and then you solve the transcendental equation graphically and count the number of intersections or count the number of solutions, and that is your answer. So it's not just easy counting. 1 2 counting, easy counting as 1 2 3. So you need to work for your number, your final answer. So of course we use graphical method to solve for the solutions of this transcendental equation. We only need the number of solutions. So that is so this is the plot of negative cotangent z. So it's actually undefined at multiple values of integral multiple values of pi. And this is still the plot of this square root of z naught over z squared minus 1. So again, at z naught is equal to z, the value is 0. At z naught is equal to z, this is 1 minus 1, 0. So in this case, there may or may not be a solution depending on z naught, because if your z naught is less than pi over 2, if your z naught is here, then there will be no intersection. There will be no solution if your z naught is less than pi over 2. So there may or may not be a solution depending on z naught. So if you will notice, the solutions occur actually at z equal to n pi. So at pi, at 2 pi, at 3 pi, and 4 pi, and so on. So let's again use the limiting cases. When you have a wide, deep well, that actually approach to the infinite square well. So your energy at the above the bottom of the well will be that of the infinite square well. And the second limiting case, if you have a shallow, narrow well, what is dilata? So if you have a shallow, narrow well, then your finite square well approaches that of the delta function well. And in that case, there will be no odd bound state actually. So just as what I have said earlier, if your z naught is less than pi over 2, there's no intersection, there's no solution to this transcendental equation, so therefore there's no odd bound state if you have a shallow, narrow well. So no odd bound state, but there is one even bound state, because if you will recall, take note, this is the limiting case number 1 corresponds to the infinite square well, and the infinite square well both have odd and even bound states. But in the limiting case number 2, that's the delta function well. The delta function well only have even bound states. So it's reasonable that you will not find odd bound states here. Okay? Okay. So that's the end of chapter number 2. So in your exam, there will be instances that the finite square well will be combined with other potential energies. So all you need to master in the topics on the Dirac delta functions and the finite square well potential is on how to count the number of bound states. That's always the problem. How many bound states? And you actually have first again to construct your even and odd solutions. So you first start with the even solutions, and then you go to odd solutions. Okay. And of course you need to set up the boundary conditions, and since these are most of the time symmetric potential energy functions, you can only use one side of the well, one boundary condition on the one half of the well, and proceed with that. Evaluate your apply those boundary conditions on your constructed even and odd wave function solutions. And of course you will approach a transcendental equation, and to solve a transcendental equation you just use the graphical method. So just count the number of intersections, count the solutions, and the number of solutions are the answer required for the problem. So we will just discuss more examples on this during our live session. So that's it for chapter 2, and I will see you again in chapter 3.